All right, today we are going to be talking about open loop operational amplifier circuits. So first, let's describe very briefly what an open loop circuit is. So if we have an operational amplifier, let me draw this triangle slightly better. Here is our non-inverting input voltage. Here is our inverting input voltage. Here is our positive power supply voltage, VCC plus. And here is our negative power supply voltage, VCC minus. Here's our output voltage, V out. So in an open loop op-amp configuration, what that means is that there is no feedback path connecting the output node to one of the input nodes. For those of you who have taken Circuits 1, you should likely be familiar with op-amp circuits in which there is some path. Here I'm going to draw it as some sort of resistor, which I'll label as RF, that connects the output node to the inverting input node. Okay, this would be an example of what's called negative feedback because the output node is connected directly to the inverting or negative input node. Open loop op-amp circuits do not contain this feedback path. So if we were to look at a signal flow diagram or a very generic amplifier circuit where we have some input signal X of t, our amplifier characterized by some gain A, and then our output terminal here, Y of t. In this simple open loop configuration, our output Y of t is simply A times the input signal X of t. So what this means is that the circuit that we looked at the end of our class meeting on Monday was actually an example of an open loop op-amp circuit. We're going to give that kind of circuit here today a name. We're going to call these circuits comparators. And this is what open loop op-amp circuits are used to do. So a comparator is an op-amp circuit used to compare the relative strength of an input voltage signal against a reference voltage signal. There are two different types of comparators, and we will look at both applications. The first is the non-inverting whose schematic diagram would look something like this. So in a non-inverting comparator, our input signal, Vn, is applied to the non-inverting input terminal, and our reference voltage, Vref, is applied to our inverting input terminal. So this circuit would have a practical op-amp model representation that looks something like this. I'll draw it over here on the right-hand side. Here's our resistance Rn. Here's our open loop gain times Vd, dependent source, where Vd, our differential voltage, is simply the potential difference across the resistor Rn, measured as the voltage at the non-inverting input terminal minus the voltage measured at the inverting input terminal. Over here, we would have our resistor R out. This is our output pin. So here is our practical op-amp model, and now we're simply going to make the connections, right? So between the inverting input terminal and ground, we have our voltage Vref, and between the non-inverting input terminal and ground, we have our voltage Vn, and our output voltage is simply the voltage measured at the output. So again, this looks extraordinarily similar to what we saw at the end of the last class. The only difference here is that we have a voltage that's connected to our inverting input pin that is non-zero, okay? So what I want us to do is spend a couple of minutes here and develop what is going to be the input-output relationship for this non-inverting comparator. And we are going to do that by simply plotting the output voltage for a few values of the input voltage and observing what happens, right? So I'm going to make my plot over here. Actually, the first thing that I'm going to do is characterize this circuit. Let's say that our reference voltage is positive 2 volts. Our open loop gain, AVOL, is 10 to the 5 volts per volt. Our input resistance Rn is 1 mega ohm. Our output resistance R out is 10 ohms. And our supply voltage VCC plus is positive 10 volts. And our supply voltage VCC minus is negative 10 volts. Okay, so we're going to have a plot. gonna look something like this. These are going to be our boundaries that we're going to talk about. Okay. So let's analyze this circuit first and figure out what our relationships are going to be. Okay. So hopefully by inspection, we can observe that our output voltage, V out, is going to be nothing more than our open loop gain AVOL times VD, which in our case is going to look like 10 to the 5 times whatever value VD has. And we can see that our differential voltage, VD, is simply our input voltage minus our reference voltage, which in this case is going to be simply Vn minus 2 volts. So from this, our output voltage, V out, will be 10 to the 5 times Vn minus 2 volts. We do need to take into account the effects of saturation distortion. As a reminder, saturation distortion simply states that the output voltage cannot be more positive than VCC plus, and the output voltage cannot be more negative than VCC minus. So we're going to make a simple table here. Vn on the left-hand side, V out on the right-hand side, and we're going to look at some values here. So let's start with an input voltage of negative 5 volts. According to our equation here, it tells us how this circuit operates. Output as a function of input. If we had an input voltage of negative 5 volts, our output voltage would be 10 to the 5, so 100,000 times Vn minus 2 volts, where Vn minus 2 volts is minus 5 minus 2, so minus 7. So we have 100,000 multiplied by minus 7 is negative 700,000 volts. Since negative 700,000 volts is much more negative than our supply voltage VCC minus, the actual output voltage is going to saturate down to negative 10 volts. So we have effectively a point right here on our graph. Now let's look at 0 volts as an input voltage. Okay. Our output voltage would be 10 to the 5 times negative 2 volts, or negative 200,000. Still much more negative than VCC minus. So our output voltage saturates to VCC minus. And I would argue that all points in between, sorry, let me express this here. This axis is Vn, this axis is V out. I would argue that if the output voltage at -5 volts is negative, at a VN value of -5 volts is -10 volts. And the output voltage value for VN is equal to 0 volts is also -10 volts. All points in between must be -10 volts as well. Let's look at a voltage of 1 volt. Okay. So at 1 volt, we are going to have an output voltage of -100,000 volts, which is still much more negative than VCC minus. So we're still at -10 volts as an output voltage. At 2 volts, we're going to have 10 to the 5 times 0, which is 0 volts. So we aren't saturated anymore because this value is actually between VCC plus and VCC minus. Let's look at what happens at 3 volts. So at 3 volts, we have 10 to the 5 times 1 volt. So this is positive 100,000. And since positive 100,000 is much greater than VCC plus, or 10 volts, we saturate to VCC plus. And let's look at what happens at 5 volts. So at 5 volts, we have 10 to the 5 times 3. So that's 300,000, which is, again, much greater than VCC plus. So we're still at 10 volts. And I would argue that we can simply connect these dots. So looking at the data points that we've collected thus far, it seems like there's going to be an abrupt transition from of the output signal from VCC minus to VCC plus somewhere around our reference voltage, right? Where this guy here corresponds to 2 volts, which is the reference voltage that we have for this particular circuit. So let's look at what happens when Vn is 1.99 volts. So when Vn is 1.99 volts, our differential voltage Vd is 1.99 minus 2 volts, or negative 0.01 volts. When we multiply that by a factor of 10 to the 5, we wind up getting a voltage of negative 1,000. So it's much smaller than what we had been seeing, but it's still significantly more negative than VCC minus. So this is still going to look like negative 10 volts. So at a point very, very close to our reference voltage, we're still saturated at VCC minus. Similarly, if we apply a voltage of 2.01 volts, our differential voltage is now positive 0.01 volts, and we should observe a voltage of 1,000 volts at the output which is much greater than VCC plus. So this is going to look like plus 10 volts. And so at a point just above our reference voltage, we've saturated at VCC plus. So if we connect these dots, what we find is that we have a nearly vertical transition from VCC plus to VCC minus. The reason why the slope of this transition is nearly infinite or almost vertical is because the linear range of an open loop op-amp circuit is so small, which is what we looked at yesterday. For a voltage gain of, or excuse me, for an open loop voltage gain of 100,000 and supply voltages of 10 and minus 10, we did the math here yesterday, or Monday, we found that the linear range was actually from negative 100 microvolts to positive 100 microvolts, which means we will only have linear amplification when our input signal is plus or minus 100 microvolts away from our reference voltage. So from this, we can approximate V out as a piecewise function. So for our generic non-inverting comparator, we will find that our output voltage is VCC plus the positive supply voltage for almost all input voltages, especially put approximately here, greater than Vref, and our output voltage is VCC minus for all input voltages that are less than Vref. So what I would like to do is actually simulate this circuit and show you what our output response looks like. So please bear with me for just a moment while I pop up to my office and grab a mouse because I forgot it again. All right, apologize for that delay. So I've got LT Spice already opened. Now I am going to open a new schematic and I am going to put down an op amp. So the op amp that I am going to use, and this is what I suggest you to use for all simulations for op amps that we're going to do in this class, is what's called universal op amp 2. Okay. So I'm going to place this op amp here in the middle of my screen. And what I'm going to do is I'm going to right click on this op amp just to talk about a few things here. Okay. So universal op amp 2 uses a SPICE model level 2 simulation of, I think it's a single pole op amp. The reason why I like this particular model is because the parameters are editable. So here on line 2, we can actually change the value of our open loop gain. Right now, it says it's 1 meg, which is 1 times 10 to the 6. So I'm simply going to right click this and change it to 0.1 times 10 to the 6, which is the same as 10 to the 5, the open loop gain for our op amp circuit of interest. Since the input resistance and the output resistance didn't actually play a role in our analysis here, I'm going to leave the remainder of the values alone. But you will notice here that you could edit the input resistance parameter. There is no explicit output resistance parameter in this particular model. Instead, you can limit the amount of current that leaves the output node of the op amp, which is just a different way of thinking about the output resistance. Okay. So I've edited my open loop gain parameter. What I'm going to do now is actually move my circuit over here to the right, and then I'm going to add in several voltage sources. I'm going to add in my power supply voltage sources first, and I'm going to show you how I do this and why I do this in a particular way. So here is going to be my VCC plus voltage source, and here is going to be my VCC minus voltage source, and I'm going to wire these two together like so, and then put my ground or reference node here in the middle. So VCC plus was 10 volts, so I'm just going to right click my voltage source and type in 10. VCC minus was negative 10 volts, so I'm going to right click this voltage source and put in positive 10. The reason why I'm putting in positive 10 is because the positive polarity terminal of this voltage source is at ground. So that means ground is 10 volts higher than the negative polarity terminal, which is giving me a negative 10 volt source. I could have simply rotated this voltage source twice to put the positive polarity on bottom and then typed in the value of negative 10, but I've just gotten in the habit of doing it this way, so I just wanted to explain that to you. Another thing that I'm going to do here real quick is I'm going to use the label node button, and I'm going to call this node up here VCC plus, and I'm also going to put that label on the power supply terminal that has a plus sign associated with it. So what this did was labeled this node for this voltage source VCC plus, and then applied that voltage to the positive power supply node of the op amp. I did this purely to make my circuit diagram more clean to look at, because if you have 4 voltage sources like we're going to have in this particular circuit, your schematic diagram can actually get pretty busy pretty quickly, and I wanted to make everything easy to see what's going on. I will also label node VCC minus and apply this VCC minus to my negative power supply terminal. Now I'm going to add a voltage source, and this guy is going to be for my reference voltage. My reference voltage was 2 volts, so I'm going to just right click that voltage source and type in 2. And then I'm going to label this node as VREF. And my reference voltage is applied to my inverting input node. Just to make myself a little bit more comfortable, I'm going to give a little stub of wire here for me to use. It actually shouldn't matter, but I think it looks more clean to do that as opposed to having the text abutting up against the component itself. So VREF is applied to the inverting input node. One thing that I do want to point out, and this is true for all op-amp models in LT Spice, for whatever reason, the positive power supply terminal is on the same side as the inverting input terminal. I have drawn our schematic representations of op-amps where the positive power supply terminal is on the same side as the non-inverting input terminal. So this is slightly different. Just remember, VCC plus should always be connected to the plus sign. VCC minus should always be connected to this minus sign, and you'll get it right. All right, our last voltage source that I'm going to use here is going to be for my input voltage. And I want my input voltage to range from -5 volts to +5 volts. So what I'm going to do is use a sinusoid with a DC offset of 0 and an amplitude of 5. So this means it will range from +5 down to -5 and back over and over and over again. The frequency doesn't particularly matter for this circuit, so I'm just going to say that the frequency is 1 hertz so that it takes exactly 1 cycle for our sinusoid to go from +5 to back up to +5. And I'm going to leave all of the other parameters blank. And then what I am going to do is label positive polarity terminal of this voltage source as Vn, and then apply that input voltage to my non-inverting input node. And then lastly, I'm going to label the voltage at my output node as simply Vout. I'm going to edit my simulation command, and we're going to do a transient analysis. And I'm arbitrarily just going to say 3 seconds here so that we'll see 3 cycles. Just place it somewhere on our schematic and press the run button. And I get a blank plot. Okay. The reason I have a blank plot is because I haven't told LT Spice what it is that I want to simulate. So first, let's look at our input signal just to verify that it's doing what we want it to do. Okay. It is ranging, that has a maximum value of +5 volts and a minimum value of -5 volts, which exactly matches what we used in our analysis. So that seems reasonable. And then I'm going to click on the output node. And here we see where our output is, okay? So if we look at this guy, what we see is that anytime our input voltage exceeds 2 volts, the output goes to 10 volts. And anytime our input voltage is below 2 volts, which is our reference, our output voltage goes to 10 volts. I can enhance this graph just a little bit here by adding a trace. So I'm just going to put VV reference to make it very obvious where our reference voltage is. So when Vn, our green curve, is increasing and crosses that red line, the output goes high. And when Vn is decreasing and crosses that red line, our output goes low. Now, this plot is different than the one we generated by hand, because this plot is a function of time. Excuse me. And the plot that we generated was Vout as a function of Vn. Well, we can replicate that plot by moving our mouse down here to the horizontal axis and changing the variable we're plotting against. So instead of plotting against time, let's plot the output voltage as a function of the voltage present at the node that I've labeled Vn. And what I'm going to do here is delete Vn, because that's just a linear line that has a ratio of 1 to 1. So Vn divided by Vn is 1. And I'm going to delete this reference voltage here. And we have the exact same plot that we generated by hand a few moments ago, where we have a nearly vertical transition around our reference voltage of 2 volts. What we can do is zoom in here. So let's make the leftmost point 2.01 volts. Let's make our plot, let's call it 10 millivolts. Actually, leftmost should be 1.99. Rightmost should be 2.01. And what this looks like is hysteresis. Effectively, it's flipping back and forth between these values. This is an artifact of us having run the simulation for 3 cycles effectively. So if I change this stop time to 1, we should only see 1 cycle. And actually 1 cycle is going to cause it to go from 0 back to 0. So we're going to see a little bit more than we need. So we actually only need half a cycle. So how I'm going to fix that is let's add a 90-degree phase shift so that instead of starting at 0, it's going to start at either negative, leave this positive 90. It's going to start at either positive 5 or negative 5. And we're going to make our transient analysis only go for 1/2 of a second. And now we only have 1 line. All of that stuff that I just did was just me playing around to make this graph look a little prettier when we zoom in. Okay, it's not remotely necessary for you guys to have to do that or really understand what I was doing. I'm just trying to make it obvious what's happening when we zoom in here. Yeah. See what's going on. How did I make the correct plot appear? Okay, so what I did to do that is I right-clicked when my mouse was down here somewhere on the horizontal axis. And then I changed my quantity plotted from time to the voltage Vn. Because quantity plotted, what it means is what are you plotting your output signal against? So if I put in time, this is what my output signal looks like as a function of time. If I put in V open parentheses Vn, this is what my output signal looks like as a function of the input voltage. So I changed my x-axis quantity effectively to make it match the hand-drawn plot that we had developed. I'm right-clicking down here now to simply change the bounds of our simulation to be 1.99 and 2.01. And so we can see we're getting we're now seeing a diagonal line. And effectively, the reason why we're seeing this diagonal line is because I've zoomed in so much, okay? When we zoom out to our original settings though, we see this near vertical transition, okay? So the linear range for this open loop op-amp circuit is so small that it looks like an instantaneous change from VCC minus to VCC plus, which pretty much exactly matches our model that we have developed, which I'll circle right here. This is the behavior of a non-inverting comparator. Now let's look at an inverting comparator. The circuit is extraordinarily similar. So for an inverting comparator, we're going to have our op amp. Here's our non-inverting input voltage. Here's our inverting input voltage. Here's our output pin. And for an inverting comparator, we apply our input voltage Vin to the inverting terminal, and we apply our reference voltage Vref to the non-inverting terminal. Now, instead of spending a lot of time going through a large derivation here, we should kind of intuitively know how this device is going to behave, right? If I scroll up here, the only difference, only difference between our inverting comparator and our non-inverting comparator is that we've swapped Vref and Vn. So the only change in our analysis is that we would have Vd as Vref minus Vn instead of the other way around, right? So effectively, Vd gets multiplied by a factor of 1, and so all of our output signals should be multiplied by a factor of 1. So what our expected plot would look like, and I'll do it over here. Here's V in, here's V out. Let's call this point VCC plus, this point down here, VCC minus, and this bit right here is our reference voltage. What we should expect to see is effectively the exact opposite behavior because we've swapped our input signal and our reference signal. So our output should be saturated at VCC plus until we get close to V reference, at which point it will switch and then saturate to VCC minus. So our output relationship here would look like VCC plus for Vn less than Vref and VCC minus for Vn greater than Vref. And we can observe that very easily on our plot by simply swapping these two signals, right? So if I apply Vref to the non-inverting terminal, and I apply, sorry, there shouldn't have been a Z there. V in to our inverting input and run the simulation, our graph flipped, which is exactly what we anticipated because we swapped those two voltage values. Does that make sense? All right, nobody's saying it doesn't make sense, so I'll assume you're on board. So the last thing that I want to talk about today is generating our reference voltages using resistive networks. So what I mean by that is we might not always have access to a 2-volt source or whatever we want to generate our reference voltage. So what we can do instead would be to use a resistive network. So let's do a little design problem here, and then I'll give you a better explanation of what I'm looking for, okay? So let's say that we were tasked to design a 1-bit analog digital converter such that our output voltage, V out, is equal to 5 volts, and our input signal, V in, is less than 3 volts, and our output signal, V out, is equal to 0 volts when our input signal, V in, sorry, I got my sign here wrong. We want V out to be 5 when V in is greater than 3, and V out to be 0 when V in is less than 3 volts. Okay. So since we are comparing our input signal to some voltage, we are obviously going to use a comparator. We want our output signal to be high when Vn is greater than our reference. So that means we're going to be using a non-inverting comparator. And our reference voltage here is obviously 3 volts because that's what we're comparing things to. So I'm going to draw what I've described thus far. So here we're going to apply V in. Here is where we're going to apply our 3-volt reference signal. This is where we take V out. So the last things that we need to do to finish up this design is to determine what our supply voltages are, right? Well, our supply voltages are going to be whatever our V out constraints are, because we know that for a comparator, the output signal is either VCC plus or VCC minus. So we want our output voltage to be 5 volts when it goes high. So that means VCC plus is going to be 5 volts. And we want our output voltage to be 0 when our output goes low. So that means we're going to put 0 volts or ground down here as VCC minus. So we've done a simple design here for a 1-bit analog to digital converter where we've assumed that we have access to a 3-volt source. But what if we didn't? So instead, we could do something like this. So what I'm giving myself up top here is effectively a 5-volt supply rail. And then I'm drawing down here my comparator circuit. And I'm going to give myself a 0-volt or ground supply rail here at the bottom. And we know that our positive supply voltage is attached to 5 volts. Our negative supply voltage is attached to 0 volts. Here's where we put our input signal, the in. And what I'm going to do for our reference signal is I'm going to just use a voltage divider network to supply that, right? So I want to make sure that I have some resistance here and here. And I want the ratio of these resistances, let's call this R1 and this R2, such that the voltage at this node is 3 volts. Okay. So there are a couple of different ways that we can approach this, but I'm going to approach it in a qualitative way more so than a quantitative way. Okay. And what I mean by that is I'm going to make an observation about the behavior of the op amp itself to guide my analysis. So if we were to look in to the inverting input terminal for our op amp, we would see an input resistance that is very large. So what that means is that I should choose a resistance R1 and a resistance R2 that is much smaller than the input resistance of the op amp. If I do that, practically none of the current that's flowing, right? So I'll have some current I that's flowing through this resistor R1 because there's a voltage drop over it. Some portion of I, let's call it I prime, would flow into the op amp, and the other portion, let's call it I double prime, will flow towards ground. Okay. I want to make this bit as close as possible to 0 amps. And I can do that by choosing R1 and R2 having a value that is much, much smaller than Rn. So effectively, this resistor network here just forms a simple voltage divider. We know that the output of a voltage divider, where our output voltage is Vref in this case, is going to be simply our supply voltage, 5 volts, times the ratio of R2 over R1 plus R2. Well, if Vref is 3 volts, we know our supply voltage is 5 volts. We need this bit right here to be 3, and this bit down here to be 5. So if we chose R2 is equal to 3 kiloohms and R1 is equal to 2 kiloohms, we satisfy all of our design constraints. Our reference voltage will be very, very close to 3 volts because R1 and R2 are much smaller than our input resistance, typically on the order of hundreds of thousands to mega ohms. So that's how we can use a resistor network to generate our reference voltages in these types of circuits so that we don't have to have access to multiple voltage sources. And just for the sake of argument, let's simulate something like that. So I'm going to close out this plot. Find my mouse, here we go. And we're going to play around with these parameters here. So let's delete this, delete this. I want my signal to go from 0 to 5 volts in this case. So I'm going to give my sinusoid a DC offset of 2.5 and an amplitude of 2.5. We'll show what that does in just a moment. I want my reference voltage in this case to be, actually, I'm going to delete this entirely, and we're going to do it with our resistor network. I'm just going to move this bit right here. And I'm going to move this over like so. So if I give myself a supply rail here, I give myself a supply rail down here, I'm going to connect this guy like so, this guy like so. I need to make sure I remember to change my supply voltages. So 5 here, 0 here. I'm going to apply my input signal. EN will go right here. And I'm going to set up my resistor network now. So here's R1. Here's R2. Let's wire things up. I'm going to make sure I label my supply rails. So this is VCC plus here, VCC minus down here. I'm going to right click my op amp and I'm going to change my input resistance. So I believe in our example, we've been dealing with 1 mega ohm. So I'm just going to right click this and change it to 1 mega ohm. And then I said R1 should be 2K and R2 should be 3K. And that should be all I need. Let's simulate this for 1 second. Let's look at the out. And let's plot it against the in. So in this design, we can see that our reference voltage is effectively 3 volts. Now, let's see what happens if I chose a 2 mega ohm resistor and a 3 mega ohm resistor, effectively making our resistor network have values on a similar scale as to our internal resistance of our op amp, right? My reference voltage is no longer 3 volts because I don't effectively have a voltage divider. I'm allowing too much current to flow into the inverting input terminal of the op amp. So that's why we want to make sure that our values for R1 and R2 are much smaller than Rn, right? So 2K and 3K gives us the behavior that we desire, but 2 mega ohms and 3 mega ohms does not, because we're allowing current to effectively get leached off from our voltage divider circuit and flow into the input terminal of the op amp, okay? The kilo ohm resistor scale is actually kind of the sweet spot for most op amp design problems. The reason why I say that is because it's about 1,000 times smaller than any input resistance you're going to see, and it's about 1,000 times larger than any output resistance that you're going to see. So typically speaking, when you design a practical circuit to utilize an op amp, you want your resistor values to be in the kilo ohm range so that you don't cause any unintended effects in your design. All right, that is enough out of me for today. If anybody has any questions, I'd be happy to answer them. If not, I will see you all on Wednesday.